Yosef, you need me to speak in English?
Yes, please.
So, hi everyone.
Hello.
As I mentioned before, I'm not sure that this course will go through as planned because there is not enough students, but we'll see about that. At least for now, let's start. Before I start, who doesn't know second quantization? Kaha kaha? Okay, so I'm going to assume that you know second quantization, and those who have trouble with second quantization, I can both send you to the book, explained there very nicely, and I can also make a note and send it out. Okay, so superconductivity is one of the most important phenomena discovered in modern science. I like to say that it's what's interesting about it is that it's important not only fundamentally, like discovering the universe is expanding or black holes, okay, and it's important not only from a practical reasons such as the blue lead or whatever. It's both. So it's something that really influenced our lives, but is also fundamentally very interesting and mysterious. So many years it was originally discovered in 1911, okay, as a exercise what to do with the new cryogenic capabilities developed, and it took about 40 years until it was finally explained. And we had a nice colloquium. I can send you also the reference to a paper. I don't know which one of you were at this colloquium, where Georg Schmalian described all the failed theories of superconductivity, which involve people like Feynman and Einstein and other people. So it was really 40 years where this was a huge problem. Everybody was trying to solve it and no one did. The reason is probably because the knowledge required to understand superconductivity didn't exist back then, so it's kind of, as they say in Hebrew, lo fail. The lo fail. Still, it's a problem that many big minds tried to deal with and weren't capable. And indeed, as we will learn in the course, so I began by saying that it's important and interesting both from practical reasons and also for fundamental reasons. But also there's another two faces to superconductivity, which is, on one hand, it's very interesting as a phenomena, okay? So, it exhibits all these magnificent things like vortices and levitation and Meissner effect and the Josephson effect and, zero resistivity and all sorts of stuff. But on the other hand, it's also very interesting microscopically. So the question of how do a bunch of electrons do what I recently wrote an abstract for a talk. How can electrons condense like bosons do? Okay, how do they end up doing something like that? That's also very surprising. And on top of all that, there's another question, which is, for example, part of the research that's done in my group is how do they condense when they should repel each other very strongly. So there's like a layer and another layer, and every aspect you look at superconductivity, it's really a magnificent topic. It's important. And then finally, maybe the last ingredient or reason why it's an important problem, in my opinion, is that it's influenced so many fields of physics. So for example, as I'm sure you know, the Higgs mechanism, which is the way particle physicists and high energy physicists understand or explain within the standard model where the mass of particles comes from, the origin of this understanding is superconductivity. Because the Higgs mechanism is actually equivalent to what is known as the Anderson mechanism, which is the Meissner. So bosons, which are photons inside a superconductor, acquire a mass in the same way that, for example, the Z and W bosons of the weak force acquire a mass. Okay, it's explained in the same, it's exactly the same mechanism. But that's just one example. Another example is the Ginzburg-Landau theory. The Ginzburg-Landau theory is now the basis, fundamental theory which we use to understand phase transitions, scaling, all this. It was developed in order to explain superfluidity and superconductivity. Okay. So, yeah, so what are we going to study in this course? So first of all, okay, so I'm going to start with, look at this in English. So I'm going to start with an introduction, which is going to be mainly a path integral formalism to compute thermal averages. 2 is going to be superfluidity, the weakly interacting Bose gas, and the superfluidity. 3 is going to be spontaneous symmetry breaking, which is another very important concept. Yeah, then we will do the Ginzburg-Landau theory. The Ginzburg-Landau theory of before this, the superconductor as a superfluid of charged particles. And 5 is going to be the GL theory. And up to this point, except for some comments in the introduction, everything we're doing is just bosons, all bosons. Then we transition and we're going to do the BCS theory, which is the first time that we're going to touch fermions in this problem. And then we will see. So I'm going to show you the Gorkov mapping between BCS and GL theories. And 8 is going to be Eliashberg theory. And then, if time will permit, and it will obviously not because we're in a short course, I want to teach Andreev reflection, and maybe 10 is Abrikosov Gorkov theory. So these are topics I probably won't have time to cover, but I would like to in the future. Okay, so any questions, comments? So let's start. So regarding books, there is a book by Tinkham on superconductivity, which is very useful. I recommend this book by Altland and Simons, which is very close to the spirit of this course. There is a book by Dejean on superconductivity. Yeah, I would say these are the main books I would use. Okay, so let's start from path integral formalism to many-body partition functions. Path integral formalism to many-body partition functions. So our what I'm going to describe now is how to compute the partition function. By the way, everyone here knows what a partition function is? Okay. How to compute a partition function using path integral formulas. Okay, and I know that some of you already studied this. To set the stage, let us consider a bunch of bosonic states which denoted by the operators AJ. So we have a bunch of annihilation and creation operators, AJ. These are ladder operators. So if you like, you can imagine that you have like a bunch of harmonic oscillators, okay? A1, A2, A3, A4, and in these harmonic oscillators you can basically occupy, you know, any number of states, okay? So for example, then I'm going to write within second quantization in Fock space. I can write some generic state, you know, 1, 3, 0, ta 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 ta, which means that let's say this is like AJ, this is AJ minus 1, this is AJ plus 1, then it's as if I have one excitation. Okay. סליחה. בינתיים אני אמשיך. דרך אגב, am I supposed to record somehow?
No, it's live.
I see. But there's someone who's supposed to... I don't know if was he here? No, not Zoom. No, never mind. There was a student who was supposed to come and make sure that everything works properly. Forgot about that. Anyways, this is a... So in the harmonic oscillator J minus 1 in our system, it's as if we have one excitation, 3 excitations in the third. So this would be equivalent to having some product where we have a dagger j minus 1, a dagger j cubed, and all this is acting on the vacuum, and I'm omitting some normalization factor, okay? Because these operators, when they act, they're non-Hermitian, basically. Okay, then in this space, what I want to deal with is what we call coherent states. Okay, so we're going to describe this path integral formalism in the language of coherent states, or path integrals between different coherent states. That's what we're going to do. So I want to remind you, what is a coherent state? A coherent state is an eigenstate of the annihilation operator. So say I have just one of these harmonic oscillators, then A acting on phi is phi times phi. This is the idea. And how do we create this state phi? A phi is equal to e to the phi a dagger times 0. And the way I interpret this guy here, okay, this is just a sum over n is equal to 0 to infinity, a phi to the n divided by n factorial times a dagger to the power of n. This is this operator. Okay? So, by the way, is there anyone who never saw coherent states? You all learned about coherent states?
You say that phi is
Oh. Yeah. Phi is, this is always...
the phi order?
Phi is the number.
So
It's a C number. Phi is a C number. Okay? And this, one can prove this. Okay? I don't know. Do I need to prove this, or you know all these? Okay, let's continue. And equivalently, we can define the state, the state phi a dagger is equal to phi star by complex conjugation. Okay? We can also identify that a dagger acting on phi is equivalent to d to d phi acting on phi. So a dagger is if you like, you can think about it that a, so I remind you that a and a dagger anti-commute with each other, okay? Have non-trivial commutation relations. So they're kind of like momentum and position with regards to each other. So it shouldn't surprise you that if phi is an eigenstate of A, then if I want to represent a dagger in this basis, it comes as a derivative. And because the commutation relation is 1 and not I, there is no I here. Which is, by the way, fine because, as you see, A and A dagger are not Hermitian operators, unlike position and momentum, and that's why this derivative doesn't come with an I, which is totally fine because it's non-Hermitian. Okay? Good. Okay, now we can also look at the product. So if I take two coherent states like this, and I want to compute the product between them, then I can use for example, I can use this equation, so I can write that this guy is theta, this guy is theta times e to the phi a dagger times 0, and now I can act with this on that. Okay, so I'm going to get, you could imagine that what I do is I write this exponent as a series. I act with each one of these a daggers on this theta. I use this equation again and again and again and again, and it's not going to surprise you that what I get is basically e to the theta star phi times 0, 0, which is just 1. So I get e to the theta star times phi. Okay, so that's the product is going to be useful for us. And what you can see here is that the eigenstates of these operators, they have a finite overlap between them. Okay, this is a very important property. It basically implies, which is not surprising, that the basis of states that diagonalizes these operators is complete over the Hilbert space. So you know that if we have a Hermitian operator, we diagonalize it, then the states, its eigenbasis, is a complete set. Right? This is a Sturm-Liouville theorem. Here, because it's non-Hermitian, we don't have Sturm-Liouville, but luckily we have that this generally cannot vanish, so it's an over-complete basis. So all it really means is that later, when we will do all sorts of projections, we will need to remember these factor in the normalization. Okay, good. So that brings me to the next point, which is what we call resolution of identity. So when we have an over-complete basis, so for a complete basis, N, right, the identity is just given by a sum over all the states n with equal weight. Okay, this is the identity. If you like, for those who just studied the course with mathematical methods for physicists, then this is equivalent to saying that a sum over what was it? Psi star lambda of x, psi lambda of x prime, right? Sum over all the states is delta of x minus x prime. This is exactly the same equation, okay? Because the delta function is like the identity matrix in a continuum. This identity here should be if n is a continuum, then the identity is delta. And this is a sum over all states. But now we have an over-complete basis. Okay? For over-complete basis, we need to oh, sorry, by the way, it's not that n is a continuum. N as a continuum is equivalent to lambda being a continuum. What's important is how we represent, so we can project these states on x. So you could imagine, applying something like x and x tag on both sides of this identity, looking for its matrix elements in this space x and x tag, and then we would get exactly this kind of equation where instead of lambda it would be n, basically just n, and like psi n of x tag is basically just oh, sorry, it's the other way around. It's like this. Psi n of x is x and n by definition. So yeah, sorry. So what happens if n is a continuum? Then this it just implies that this sum needs to be considered an integral, and that's indeed what we have here, because remember that these phi's are C numbers, so they are a continuum. So this is a very long story. We need to normalize by the overlap. So we have something like this. The identity is equal to an integral d phi star d phi divided by pi e to the minus phi squared phi phi. And the idea is that you can verify that this is an identity, okay, by doing the same kind of trick as here, for example. Okay, so we can project. The best way to do it is actually not to use a position basis, but to use the Fock basis, n. So if you use the Fock basis, I have a proof in my notes. I can show it to you if you're really interested. But basically, you could imagine computing this matrix element, which would be the integral d phi star d phi divided by pi e to the minus phi squared of n phi phi n. Okay, and then we can interpret these guys by using
which one is n pi?
What?
N pi, right?
N phi?
No, n pi.
N prime. Sorry. So we can interpret these guys using basically by expanding this way, and then we have an overlap between states, right? You know that in the Fock basis, n and n prime is equal to delta n n prime. Yeah. Yeah, and actually there's another, maybe I'll give you a hint. Wait, you don't see here, right? So I'll just give you a hint that one can prove that m times phi is equal to phi m divided by square root of n factorial delta m n. Basically using this. So then you can compute these exactly, and you can show that you get the identity.
Then?
What? Not delta n m. What am I saying here? Sorry, no. You get this. Yes. So By the way, because Joseph speaks English, it's better if you... I'm not talking in English for no good reason, but I'll explain. We're basically asking why we have two integrals. He understands Hebrew, it's just that sometimes when we talk too fast, it's hard for him to catch up. So you have to remember, so this is a C number, phi, right? So it's a two-dimensional complex plane. So you can do the two-dimensional integral any way you like. You can do, for example, you can call the imaginary part y and the real part x, and do an integral dx dy.
Oh, that's another basis, like not the...
Yes, exactly. Or you could use other variables. You could use x plus iy and x minus iy, and they're still, independent variables. So this is a complex, standard complex integral. Okay. Let us see what is the next topic.
In the hint you gave us, m is the number of particles in a state?
No. Okay, this is... So, first of all, right now, I'm talking about a single harmonic oscillator. Okay? And this state M is a state of the harmonic oscillator with M excitations. So just for clarity, if I were to compute M times X, or the other way around would be better, although it doesn't matter actually, then this guy would be, I'm not sure I remember correctly, but it would be the Hermite polynomial of order M times e to the minus x over, well, that depends on the length scale, but let's say you don't have any length scale, something like this, 2m. I don't remember actually the harmonic oscillator states, but that's what I mean by this. It's been excited, you excited the harmonic oscillator m times.
And phi is just an eigenstate of A.
Phi is a coherent state. Yes. Okay. So the overlap between a specific Fock state excitation and the coherent state is given by this. Okay. So now remember that when I started, I didn't want to think about a single bosonic state. I wanted to talk about many of them. Why many? Well, we're going to talk about superconductors, and in a typical superconducting material, you have an Avogadro number of particles, and a similar number of Cooper pairs, which are bosons. So obviously, we want many bosons. Okay, so to generalize that, I'm going to promote phi to become some sort of vector. So you could imagine that phi is actually equal to phi 1, phi 2, phi 3, okay? Remember that we had these harmonic oscillators. I'm going to draw them again. We have 1, 2, 3, and in each one of them I can have many excitations. I can actually have in each one of them some coherent state. Okay?
They're independent.
What?
They are independent.
They're independent in the sense that they are different Hilbert spaces. I don't know what do you mean by independent?
They can't interact with each other.
They can interact with each other. I'm not saying that. But I'm constructing, this is at the level of constructing a Hilbert space. So this would be a tensor product of, the Hilbert space of this times the Hilbert space of that times the Hilbert space of that. So a general wave function, for example, would be a product, a sum over, say, products, or I could construct, okay, let's put it this way. I could construct a basis of states for which I can span any wave function in the Hilbert space as a product of, states of 1, states of 2, states of 3, and so on and so forth. So, for example, any wave function would be represented by, you know, some configurations. Let's call them nj, okay? And then cn1, n2, and I don't know how many states you have, times n1, n2, and n. Okay, like this. And these are, each one of them is like a Fock state. Okay? And when I write this like that, I want to imagine that in each one of these harmonic oscillators, I have a coherent state, and the coherent state has these C numbers representing it. Okay? So how do I, so all the equations I showed you, how do they generalize to this many-body state? So this is basically the bottom line. So we have phi is equal to e to the sum over j. Phi j, a dagger j, 0. This is the generalized coherent state. Now we have any number of these states. And similarly we have this. Oh, sorry. And then we have phi, say theta, like, or before we wrote it like this, we wrote theta and phi. Then this would be like e to the sum over j theta star phi j, which is like product, and then the resolution of identity
still before second quantization and still one particle per oscillator?
We're not before second quantization because I said I'm going to assume that you know second quantization.
No, I mean, did we already use it?
In a sense, once we think about bosons filling these states, we're already working in second quantization. But I agree with you that the way I presented it is a way in which even someone who did not learn second quantization can actually understand second quantization, because once I say that, you know, it's just a bunch of harmonic oscillators sitting, you know, I say, let's imagine that you have a bunch of harmonic oscillators on a line, okay? And that's a way to explain, that's like a poor man's way of deriving second quantization, because what is second quantization? Second quantization is saying, let's represent particles as excitations of, you know, something like a harmonic oscillator. So let me just complete. So this guy is going to become now an integral d phi star and phi, and I'll explain what that is in a moment. E to the minus sum over j phi j squared phi, okay? And this d phi guy, d phi star phi, is just a shorthand notation to a product over all these j's of d phi j star d phi j divided by pi. By the way, each one of these guys is divided by pi because the Gaussian integral, right, in 2 dimensions gives pi. Right? In 1 dimension it gives square root of pi, in 2 dimensions it gives pi. So this is why this pi appears. Good. Okay, so now let's write a expectation value observables of operators. Which is going to be very important for us to construct the path integral. So let's imagine the operator H, which will be something like d dx, a dagger of x Okay, what we have here is a Hamiltonian, okay, written in second quantization. Now, again, if you have a difficulty with second quantization, you can imagine that this is just a bunch of harmonic oscillators, but instead of have a discrete number of harmonic oscillator, I assume I have a continuum. So each one of these creates a boson at location x, and I represent the Hilbert space in a way that basically it's like Fock states, where all I really care about is how many bosons I have at each location in space. And what this operator does, it gives me the energy of a certain configuration of these bosonic excitations. This term is what we call the kinetic energy, right? So this would be like p squared over 2m. H bar is equal to 1. Okay? This is the chemical potential, which is one of the reasons that we even go to second quantization, because as you know, it's much easier to work in the grand canonical ensemble and not the canonical ensemble. Second quantization allows us to do that, because when you learn about first quantization versus second quantization, then in first quantization we can write wave functions for n particles, fixed. It's not easy to write wave functions that can generalize the number. It becomes very cumbersome to work with different particle numbers. So this is the free part, the quadratic part. You can name it, you can give it many names. And this is the interaction. So we're assuming two-body interaction, generic two-body interaction between these bosons.
You mean that what you wrote there is the expectation value of H, right? No.
This is not the expectation value of H. This is the H, the operator. We're now going to,
okay.
That's our objective. So you understand that if I take an expectation value of H, I'm going to obtain some expression, some integral over these fields phi. Okay, which represent coherent states. So now imagine that at each location in space, I have a boson, I have a harmonic oscillator, continuum of harmonic oscillators, and each one of these harmonic oscillators can be in a coherent state. And it turns out that it's extremely convenient to represent everything in terms of coherent states, because then we will be able to convert it to what is known as path integral. Okay, over configurations of these.
That's actually why all the A's are to the right, right?
Okay, so that's another issue, that this operator is what we call normal order. We are going to assume, like, the whole derivation is going to work only for normal ordered operators. If they're not normal ordered, we need to normal order them. And there's a here it's kind of straightforward, but there is a more general formalism how to normal order operators. If you have trouble with that, then just know that if there is any, let's put it this way, if there is any ambiguity how to normal order an operator, like for example, imagine that you don't have just simple products like this, you have functions of operators and stuff like that. There is a way of doing that, okay? And we can discuss that need be. But right now, yeah, that's an important point. What I'm going to show you works for normal ordered operators. Okay, so this is the Hamiltonian. And now what we want to compute is, say we want to compute something like the energy. So something like, yeah, so now, okay, and our states are, so psi, remember that psi is going to be a coherent state at each position. So before we talked about phi 1, phi 2, phi 3, but now we have a continuum of these phi's. So how does that work? So that works like this. We have e to the integral d dx over all the possible psi's, psi of x, a dagger of x. So generalized is quite straightforward. And now say we want to compute something like psi h psi. Now this naively gives you the energy, but this is not an energy, right? Because psi is not normalized. So in order to compute the energy within psi, we need to normalize the wave function, because we saw that because it has this, well, it's just the states are not normalized on top of the fact that they're over complete. And now we can just use the identities that we've developed, and then one finds that this is basically becomes a functional of these fields psi star and psi, which represent a configuration and is given by integral d dx, and we have psi star minus Laplacian over 2m minus mu psi of x. This is psi star of x. And same we have for the interaction. Integral d dx prime x prime x okay, and then okay, so yeah, so in general what you see is that if you compute some expectation value, then it becomes a functional of psi star and psi.
What do you mean when you write ddx? Is it Einstein notation?
You're asking what is d to the dx? No, it just means that this is for general dimension. I didn't tell you what x is. Now let's discuss trace of operators. So trace by definition, okay, by definition is a sum over states n, o, n. That's clear? That's obvious? Where n here, n is again, you can think about it as the Fock space, but actually n can be any complete set of states. Okay, in the sense that, yeah, that it's a complete set. Okay? Now we can stick in the resolution of identity. Okay, so we use the resolution of identity that we've derived, and then we get a sum over n, integral over d psi star psi exponent of minus psi squared. Now this should be read as an inner product. Okay? So for example, if we have a continuum of harmonic oscillators, then this guy is actually an integral over x. Okay? So when I write psi squared, it's like psi the vector star, or psi, basically psi dagger psi. Okay, and if these are a continuum, then this is an integral d dx of psi star of x, psi of x. Okay? If we have discrete bosonic states, then this would be a sum. Okay? So this is just a comment. Okay? And then the last piece is n psi psi n. Oh, wait, I forgot O. Most importantly. So we have O, and then we have N. So basically you can see that we just stuck in here, we just stuck in this resolution of identity. Okay? We plugged it in there. Okay? Now let's shuffle things around. Let me move this. This is a C number, right? This is a C number. Okay? So I can, C numbers commute with each other. So I can take this and put it here. So I can rewrite this as question?
No.
I can rewrite this as e to the minus psi squared, and then I write a psi, and then I have something like sum over n and n o psi. Right? That's always on the other side. Not that it matters, because this is the identity and everything commutes with the identity, but just to be 100% transparent, let me write it like this. So I move this to the other side, and I move the sum in here, and I get this. And this guy, by definition, is just the identity matrix. So it doesn't affect anything. I can just move it. And then I see that the trace over an operator O is nothing but the integral d psi star psi e to the minus psi squared O of psi star and psi. Okay? So what we find is that we can, if we know these functionals, then we can represent quantum traces as integrals over these fields. Okay. Any questions about that? Okay. So now we're going to switch gears and go to fermions. All this was for bosons.
What was the big the on the what exactly did you move?
Here,
Yes.
this is a C number. This expectation value is a C number, and this expectation value is a C number. So I just commute them.
Okay.
טוב, עכשיו דברים מתחילים להיות קצת ביזאריים, כי אנחנו רוצים להתעסק בפרמיון. עכשיו, so now things are going to get a bit weird, because we want to deal with fermions. The basic idea is the same. Okay, we still want to represent the field within second quantization using ladder operators. Okay, so we have these guys C and C dagger in the way that these are annihilation and construction or creation operators of some fermionic state. But what's different between a bosonic and fermionic part? So yes, so okay, so good point. So if for bosons we had that A dagger, which is equal to A dagger minus A dagger A is equal to 1, then for fermions we're going to use anti-commutation relation, which is C dagger plus C dagger C is equal to 1. Okay? Basically the point. And you can convince yourself that this is what you need. Now, if you want a hint for where this is coming from, it's basically coming from the symmetrization of the wave function. So I'm not getting into second quantization completely, but I want to remind you that the point is we want to think about so it's not, by the way, it's not only this, it's also, you know, that A dagger, sorry, maybe, let me make a comparison. So, say we have the fermions, and we have bosons. So on this side we will have that C J C dagger I is equal to delta Aj. Then here we have A J A dagger I is equal to delta Aj. But then remember that we also want something like Aj AI or A dagger J A dagger I to be equal to 0. Here we're going to have the same relation, just with anti-commutation relation. Cj Ci is equal to 0 and Cj dagger Ci dagger is equal to 0. So you can work out the fact that if I create a generic state using these creation operators, okay, by applying many of these A dagger J's, and then projecting this onto real space wave functions, you're going to find that what's nice, and this is actually the reason why we go to second quantization, is that the form of the wave function that we obtain is symmetrized. In the sense that if I have some generic state, imagine that I take something like x1, x2, x3, n1, n2, okay, some state created by these operators. This will be something like psi of x1, x2, x3, okay? What you're going to find about this wave function is that this wave function it's symmetrized in the sense that if I exchange the position of these two particles, what does this wave function mean? This wave function means that the first particle, which I label somehow, is located at position x1. The second particle, and it doesn't even matter how I enumerate them, is located at x2, and so on and so forth. If you create, using only these operators, a wave function, or any sum of them, you're going to get a situation where when you exchange two of these particles, it will be equivalent to exchanging two of these operators. And you can see from this relation that A dagger J, A dagger I is equal to A dagger I, A dagger J. Which means that when you exchange the two, you get the same sign. Which means that the wave function is symmetrized. Now, why is this symmetrization so important? Someone wants to remind me, why is it crucial for me the wave function would be symmetrized?
For the Pauli exclusion principle.
Well, here we're talking about bosons, so there is no Pauli exclusion. What do you mean by parity?
This is the position of bottoms that they are. That if you switch.
No, this of course we know that bosons should be able. But I'm asking why? Why physically do I expect it to be able?
So you can distinguish.
Again?
You can't distinguish.
Yeah, I can't distinguish between the particles. See, it's not like one particle is called Yossi and the other one is called Rachel, right? I can't start distinguishing them. And if I get a situation where I exchange I put instead of this particle here and that particle there, I switch between them and I get a different wave function, that's obviously outside the scope of physical states. And that limits the wave function by a lot, right? Because if I look at the space of all possible wave functions, it's much, much bigger than this symmetrized wave function. So this is a limiting factor, very hard to take care of in first quantization, and this is basically the reason why we go to second quantization. Now, the point is that because all observables in quantum mechanics, due to many different reasons, come as products of psi star and psi, then generally you don't really need this wave function itself to be symmetrized. It can also be anti-symmetrized, and that is the case of fermions. So that's what makes the difference, and you can immediately also identify the property of Pauli exclusion from this, because if you take two of these coordinates to be equal to each other, then the exchange between them needs to take you to minus yourself, but basically it's the same point. So it means that the only way the wave function can remain the same but also be equal to minus itself is that it vanishes. So this is the story of why we use anti-commutation relation. It gives us the right algebra. It constructs states that have the anti-symmetrized property, and also you can see that from this last condition we see that C dagger J squared is equivalent to 0. Okay? And this is also important because it limits the Hilbert space of each fermionic state to be either 0 or 1, instead of like a boson, which can be occupied by many states. Okay? Now we want to write coherent states for these operators. Okay? So I'm going to assume that I have some coherent state some coherent state eta, such that C eta is equal to eta eta. Okay? That's all fine. But you can already see that there is something weird about these wave functions. For example, imagine that I look at C squared eta. Okay? On one hand, due to this condition, this is 0. Okay? But on the other hand, this should also be equal to eta squared eta. Right? So it means that these etas, it's not going to really work out for us. It's not going to really work out for us if we take them as C numbers. We could also do something else. We could look at something like C dagger 1, C1, C2, eta 1, eta 2. This should give us eta 1, eta 2, eta 1, eta 2. But on the other hand, okay, this should give us a minus C2, C1, eta 1, eta 2. By commuting the two, I collect the minus sign. And this gives me, if these were C numbers, if these were, okay, you know what, let me just write it this way. Then I'm going to get minus eta 2, eta 1, eta 1, eta 2. Okay? So you see here that this is equal to minus itself if these are C numbers. Again, basically what I'm emphasizing is that we can't get around constructing coherent states for fermions with C numbers. It's just not going to work. Okay? What we need in order to construct coherent states for fermions, we need numbers that anti-commute. So we need something like eta 1, eta 2 is equal to minus eta 2, eta 1. Or if you like, eta 1, eta 2 is equal to 0. So, and it turns out, this was developed before quantum mechanics, that mathematicians have defined numbers like these. So if you want to know, where something like that could come, so when mathematicians define the field, the field of numbers, then one of the conditions is, of course, commutation. Okay, this is one of the basic properties of a field. Okay, and mathematicians tend to ask themselves, what happens if I relax such conditions or modify them? And in this case, they constructed these kind of algebras for objects where instead of commuting, the objects in your field, they anti-commute. And these are called Grassmann variables. So mathematicians already define them, and they're very funny numbers. So let me quickly go over their properties of these weird Grassmann variables. We're only going to need them in order to construct the field integral for fermions. Okay, but once we're not going to use them really that much, so don't get intimidated. A function of these Grassmann variables should be interpreted through the so let's say I have n Grassmann variables, so I can Taylor expand the function. So I'm assuming this is an analytic function. I don't know how to write a non-analytic function of Grassmann variables. Then I write dn f to d eta 1, d eta 2, d eta it's let's call it J1, J2, and Jn, whatever. And then we have eta of J1, eta of J2, eta of J3, eta of J. And so this is 1, 2. We have the property that d eta j to d eta I is equal to delta ji. So if I take a derivative with respect to a certain Grassmann variable, then this is what you know. This is the derivative you know and love. So we have for integration, we have that the integral d eta I is equal to 0, but the integral d eta I over eta I is equal to 1 of all things. Okay? So Grassmann variables anti-commute with operators. So Ci eta j is equal to 0.
Anti-commute. No.
What?
Never mind.
Oh, by the way, there's something I forgot. Oh shit. I forgot something. How did I forget this? Comment. Sorry, I forgot. This is related to the bosons before. I just forgot about this. Imagine that I want to compute something like a d phi star phi. D phi star phi. Okay, of e to the minus a phi star a matrix phi. Okay. This is what we call a Gaussian integral. how do we compute this? So first of all, what we mean here, this is an integral, to remind you, this is an integral d phi star j, d phi j. We have pi j, okay, divided by pi of all things. And here we have minus sum over ij, a phi star I, aij, phi j. Okay, this is what we have. So how do we compute such a Gaussian integral? Do you know?
Taylor send it?
Taylor expand. No. We want to use the Gaussian integral. By the way, it is important that aij is a symmetric matrix. Yes. What?
No, you have to use to diagonalize it, right?
Yes. So if aij is a symmetric matrix, and let's assume for a moment that it's not only symmetric, it's Hermitian, then you can diagonalize it with an orthogonal transformation. Why is this important? It's important because then we don't have any... first of all, we have well-defined fields which don't rotate into each other. They stay orthogonal. And the second, that's orthogonal. And the second thing is that we don't have any Jacobians. Okay? So we assume that, you see, W dagger A, W, okay? This thing is equal to some diagonal matrix D, and D is something like, you know, epsilon 1, epsilon 2, epsilon n, I don't know, something like that. Okay? So what that means is that I can stick this W here and W there, and I can redefine W dagger phi. I can call this, let me call it, I don't know, let me call it psi. Okay? Then this integral becomes integral, a sum over j, okay? D psi star, d psi j divided by pi, e to the minus sum over j epsilon j psi j squared. Okay?
Don't you count things twice?
What do you mean by that?
In the summation at the exponent?
This?
Yeah.
Oh, this is a matrix. This is a general matrix.
Yeah, but you want phi I and phi j. You sum of them. Don't you count both I and j twice?
I don't understand the question. First of all, there is no... Look, this is a matrix. So what I wrote here is just explicitly... Remember that phi is a vector. Okay? So, but yeah, by the way, I should write here dagger. Dagger. So this is just writing this explicitly. There is no question about summing things twice. This is what this means. Okay? But once I diagonalize this matrix, okay, then it assumes this form. And now each one of these Gaussian integrals will give me a factor of pi. Okay? So that cancels. But I'm going to get 1 over the square root, sorry, not 1 over the square root, 1 over epsilon. So I'm going to get a pi, j is equal to 1, I don't know, up to n, 1 over epsilon j. Okay? Yes?
How did you diagonalize it? Didn't we have other complete bases? This method?
First of all, you're talking about something completely different. You're talking about the space of a coherent state wave function.
So this is general.
Here, I'm talking about a matrix.
Okay.
This is a finite matrix. and I'm assuming that this matrix is Hermitian. Okay? If A is not Hermitian, it's a little bit more complicated, okay? But it needs at least to be symmetric. If it's not symmetric, it's a mess. Okay? Okay, but let's go back to this. Now you get this, okay, just by Gaussian integration. And as you know very well, I'm sure you know, the determinant is just the product of the
It's 1
eigen.
over the
What?
It's 1 over the
Yes, exactly. So what we get here is 1 over the determinant of A. Okay? And this is the important relation I wanted to say. So just to summarize, the integral d phi star phi e to the minus phi star A phi is equal to 1 over the determinant of A. So this is what we have for bosons.
And for the terminant, we will get the terminant.
No.
Okay.
But that's by the way, the permanent does show up in the relation between fermions and bosons, but a different place. So if you want to represent the many-body wave function of fermions, you can represent it as a determinant called a Slater determinant. Okay, of single particle wave functions. A Slater determinant of single particle wave functions. And the reason we use a determinant is because a determinant has the property that any any permutation, like every term in the sum, comes with the sign of the permutation, and that's exactly the it gives you exactly the anti-symmetric property of fermions. So in that case, you can ask yourself, how will the wave function of bosons? There you have a permanent. So the wave function of the bosons looks like a permanent. And I also want to point out another thing which is kind of interesting, is that you can have situations where when you have fermions, you can have like, this is also important for superconductivity, it's worth commenting. We're going to have in a moment, okay, let me write first of all the Gaussian integral for fermions, and then I'll make another comment which is along these lines. So 5 is Gaussian integral. So what we have is an integral d eta bar d eta, and here when I write bar, it's not the complex conjugation. It's basically two Grassmann variables. Two different Grassmann variables, fields, which are related to each other, okay, through the Gaussian integral. So say we have something like A eta, okay, then how do we do this integral? Now say the same response you had before.
Taylor.
Yes, now you Taylor expand. Why? Because eta squared is equal to 0. Eta squared is equal to 0, then the Taylor series is very simple to do. And this is kind of very characteristic of Grassmann variables. Although they sound intimidating and weird and different and unintuitive compared to real numbers, actually the algebra with them is much easier. Okay? So all functions are linear. Everything is super easy. Okay? So we get that this thing is equal to an integral d eta bar d eta, and then we have 1 minus eta bar, A is a C number. C number. Okay? A eta bar eta. Why? Because all higher order terms just vanish by definition. Now, what we can do is, okay, so the first one you see is the one here vanishes obviously. So what we're going to have is we're going to have d eta bar minus. This is equal to minus a, the integral d eta bar d eta, eta bar eta. Now I'm going to exchange this d eta with the eta bar. I'm going to get a minus sign. Okay? So I'm going to get a, the integral d eta bar, the integral d eta eta, which is just a. Okay? And from here you can convince yourself that for bosons, for fermions, the equivalent of this equation is that d eta bar d eta e to the minus eta bar a eta is not the permanent, but the point.
Can you look back here?
Ah, right. Okay. So let me do the same exercise now for Grassmann variable.
So the switch you did at the Gaussian integral is between eta bar and d eta. This is what you switch them that caused the minus.
You're asking where does the minus sign come from? Yes, because d eta and eta bar anti-commute. Okay, and here what I mean by this, I mean pi. So d eta bar eta is a pi d eta bar d eta. So unlike the bosons, there is no factor of pi here, because the Gaussian integral doesn't give pi, it gives 1. So imagine that if a was 1, I don't get pi, like in bosons. Okay, then as before, I'm going to make a transformation. So I define a W dagger eta. Let me define that as my psi now. But this time psi is not bosonic, it's fermionic. So I get an integral d psi bar psi e to the minus a sum over j epsilon j a psi bar j psi j. Okay? And then this guy gives me pi over all j epsilon j, because I just do them one by one like this guy here. Okay? So this guy gives me now, instead of 1 over the determinant, it just gives me the determinant of A. Okay, so this is the difference between bosonic Gaussian integration and fermionic Gaussian integration. Okay? For fermionic Gaussian integration, I get det of A. For bosonic Gaussian integration, I get 1 over det A.
Can you explain what was eta bar?
No. No. So, yeah. So, the way we want to think about it is this. Remember that we start from something like this. Let me erase this. We start with something like C, right? Eta is equal to eta. Okay? Such that we want oh, sorry, what am I doing? Such that we want eta C dagger to be equal to eta bar. Okay? But you see, the problem is that I can't just complex conjugate eta because it's a Grassmann variable. So yeah, I guess yeah, let me think about this. What would be a good way of explaining this? Yeah, by the way, I didn't, let me see. I didn't really explain to you yeah, so let me get back to you. I'll try to explain why this eta cannot be viewed, but you can almost view it like a complex conjugation if you could do such a thing to a Grassmann variable compared to eta. So there is some relation between them, but yeah. Yeah, there is some relation coming from this relation, which I demand. So if I can perform a complex conjugation on this, I want to get eta. Yeah, let me get back to you. To be honest, I'm not a mathematician, so I don't know why it's important to insist that this is not exactly complex conjugation. But we can discuss that. Okay. So there is some, let me see, what else? Okay, so, and then let me, okay, and then, yeah, maybe this was a bit too, okay, so we did Gaussian integrals. Let's see if we need, the rest kind of follows through. So expectation values of operators and trace works in the same way. Resolution of identity works in the same way. So if I have something like eta 1, eta 2, yeah, then I can write this as eta 1 e to the minus e to the minus eta 2 C dagger 0, and which gives me e to the minus which gives me eta 1 e to the C dagger eta 2. לא, מה פתאום. And then this, he gives me, you know what, let's compute this actually. Let's compute this exactly. So I think that what we want to say is that this is equal to 0 e to the, let me see. So this is e to the minus c eta bar, e to the minus eta, this is eta 1, this is eta 2 c dagger 0. What? And now these we can expand them, okay? So this guy is like something like 1 minus c eta bar 1. Right, and this is 1 minus eta 2 c dagger. And this is 0, and this is 0. So, so we have what the one gives us 1 here and 1 there, and then we have this guy. So we have plus 0, and then we have c eta bar 1 eta 2 c dagger. So I can commute this twice, once and twice. So so I can write that this thing, so imagine that I move this here, I get 1 minus sign. Then I move this here, I get another minus sign. So I'm going to get 1 plus eta bar 1 eta 2, 0 c dagger 0. Is that right? And then I can commute these two. Okay? And then I'm going to get 1. So, right, c dagger is equal to minus c dagger c plus 1. Right? Yes. So then this guy gives me 1 plus eta 1 bar eta 2, which is equal to e to the eta bar 1 eta 2. Although I think, yeah. And I think that's what we want, right? That's what we had before with the bosons. Yes, okay. Okay, so that's clear. So basically what I'm trying to say is that all the relations we saw before. So remember that before we had something like theta phi is equal to theta star phi, right? So here it works the same way.
What did you do with the c dagger?
What did I do with the, oh wait a second. So yeah, so one important comment, wait a second. Yeah, one important comment is indeed that you define these with a minus sign. But I don't think that's very crucial here. Yes, what was your question?
You said c dagger equal 1 minus c dagger.
No, I'm just saying that this guy, I can substitute c dagger is equal to 1 minus c dagger c.
And the c, because the
c kills it.
Okay.
Annihilates the vacuum.
And the 1.
The one
Tiny one. Okay.
the one gives me 0 vacuum expectation value, which is I assume it to be normalized. Okay, good. So now we can continue. We can finally do the field integral. Okay, so all this was an introductory to the math we need in order to compute the field integral. Okay? Now we can do the field integral for both bosons and fermions. Okay. So what do we want to compute? So we want to compute this guy, which is the trace of e to the minus beta h, for example. Okay?
Why is that? Why is the trace?
Like summing in
Why is it the trace? First of all, this is by definition the partition function of a quantum state. One way you can view it is imagine that you diagonalize h.
Okay.
I don't know how you diagonalize them, but let's assume you diagonalize them. Then you can always write this. You can use the eigenstates. So let's say that you have h acting on j is equal to ej j. So you have these eigenstates. Okay? Then you can use them to compute the trace. Because h is Hermitian, then the set that diagonalizes is a complete set. Okay? So the trace is just by definition, it's equal to j e to the minus beta h j. This you agree?
Yeah.
Now I can add with h on this. So I get a sum over j
Right.
e to the minus beta ej.
All right.
And ej is the many-body, if it's a many-body system, it's the many-body energy of the Hamiltonian. So it just gives a weight. Each configuration gets a weight and the partition function corresponding to its energy, which is, I think, the correct interpretation of the quantum state in statistical mechanics.
And
Okay? And beta, by the way, if I didn't, is 1 over t.
k equal 1.
K Boltzmann is equal. No, that's of course a joke. Yeah.
And is there an identity that the trace is constant under transformation?
And the base of
Yes, of course.
Yeah.
Because any matrix, right? If you take a trace of a matrix A, right? You can always put in any orthogonal transformation W. Let's for a moment assume it's even a Hermitian matrix. Then this is equal by cyclicity, by the cyclic properties of the trace, right? Because I can move this here and they cancel each other and I get the same. So the answer is yes. The trace doesn't depend on the basis. So what we're going to do is Therefore, let us use the Fock states to compute the trace, which implies let me write the trace Z as a sum over n e to the minus beta h n. But as before, we saw that the trace can be computed by sticking in a resolution of identity, which is equal to what is it equal to? It's equal to an integral d psi bar psi, and here I'm using the bar notation such that it can be either fermions or bosons. Okay, e to the minus psi bar squared psi psi. What's the question?
What notation did you mean?
The bar here. It's, for bosons, it's just simple complex conjugation. Okay, and then this guy becomes an integral d psi bar psi e to the minus psi squared sum over n n psi e to the minus beta h n. Okay? And now I want to do the same trick as before. I want to get rid of the sum over n by isolating in the identity matrix. But notice that when I switch places here, then if these are bosons, then this is a C number and this is a C number. But if these are fermions, then this is a Grassmann variable and this is a Grassmann variable. By the way, maybe we should verify that within Grassmann variables n eta, okay, this is like having n, and then we have something like 0 minus eta 1, okay, and then what we get here is delta n0 minus eta delta n1. So yeah, so you could imagine that when you take this, so that implies that n eta eta 1, eta 2, n, okay, then this is equal to delta n 0 minus eta 1 delta n 1 times delta n 0 minus eta 2 bar delta n 1. Okay? And now when I exchange between these,
Do you need to exchange?
yeah, I want to exchange between them. I want to argue that, okay, so let's see. So this gives me this times that, this times that gives me a plus. Minus. Yeah, maybe a better way of writing this. Hold on. Let's write it like this. So let's write n psi psi n. Okay, just for the fun of it. Then this thing would be n, and then we have 0 minus psi 1 times 0 minus psi bar 1, and then this whole thing has 1, and then this guy is n. So now I can open up all these things. So this is going to be 0, 0 minus psi 1, 0 minus psi bar 0, 1 plus psi bar 1, 1, 1. Okay, but because we work only with normal ordered operators like h, they do not change the number n. Okay, and then therefore these terms do not contribute, and we can overall so this is n and n. So we're computing this within the same n, and you might worry about, wait a second, here you have an operator, but remember that this operator is normal ordered, so the overall n doesn't change. Yeah, wait a second. Actually, no, that's not true. No. That shouldn't matter.
You have the same n, it must cancel, right?
Yeah, here it's definitely true that if I continue, then this thing is equal to n. Indeed, like these vanish in this case, and I have something like 0. Then I have something like I'm gonna have something like n times 0 minus psi 1 psi bar wait a second this then becomes 0 plus psi bar 1 times n and 0 minus psi 1. Okay, now why? Because let's see if this holds in all cases. Because if n is 1, then we get psi bar psi with a minus sign, which is what we should get, because if you commute the 2, then you get a minus sign. If n and n are 0, you get 1, which is indeed what you should get here, because 0, 0 gives you 1. But there is a problem. I'm kind of concerned about h, because h can shift between the different. So I'll have to get back to you exactly why. But similar to this idea here, okay, in the same spirit, when I take this through, I need to remember that these psi's here are Grassmann variables. And they will interfere with these Grassmann variables. So what we get is that this guy is equal to d psi bar psi e to the minus psi squared. And then we get a zeta psi, which I'll explain in a moment, sum over n e to the minus beta h, sum over n, psi, like this. And then this guy is just identity, so I can throw it away. And in the bottom line, what I get is that the partition function z is given by an integral d psi bar psi. Question? This? It didn't explain it. I'll explain it in a moment. It's zeta.
אם זה בוזון, זה 1, אם זה
Zeta psi e to the minus beta h psi, where the zeta is equal to 1 for bosons and minus 1 for fermions. And I owe you an explanation exactly why it works even when we have this e to the minus beta h term.
Why is there a minus sign in the before the integral? A line before the integral? Ket of 0.
Why is there a minus sign? A line before the integral. Here? Here?
Yeah.
Why is there where a minus sign?
Before the psi.
Here?
No, very well.
Here?
Yeah.
Well, that's kind of the point. The point is that when I exchange these two, one of them collects a minus sign. That's exactly this zeta here.
But this one doesn't.
Yes.
Above you had it. One of them changed sign and one didn't.
Again, if they both had plus here, I wouldn't get the right result. Let's look here. If n is equal to 1, I get minus psi times minus psi bar. I get psi bar. Okay? And that should be equal to minus psi bar psi, because these are fermions. Okay? I should write here, this thing, this is 4 fermions. Okay? Okay. So this is the first step. Now the second step, okay, so this is the first step we need in order to compute the field integral. The second step is, as you know, first of all, is there anyone here who never saw path integrals develop? You also didn't see? Path integral, Feynman path integral, no. So the idea, so those who saw it last year, the idea here is similar. We're doing it many body instead of single particle. So in the single particle, just to kind of get you up to speed, in the single particle business, you have something like e to the minus e to the minus I t h, and you compute it between x2 and x1.
T is the time.
T is the time. This is just evolving in time. It's like starting a particle at a well-defined delta function in x1, evolving it. You can imagine that when you evolve it in time, it spreads out, okay, due to the it's like evolving with Schrödinger equation.
Okay.
And then you're computing the overlap at point x2. So it's basically like asking, what is the probability of finding a particle at x2 after time t if it started at position x1? This is how Feynman constructed the path integral. And the first step that he did, okay, this quantity in the end becomes an integral over dx. Let's call it dx, where x is now a field. So these are fields of t. Okay, where x of t1 is equal to x1 and x of t2 is equal to t2, e to the minus I s of these x of t, something like that, and h bar is equal to 1. So this is, and this s here is the action of the path. So you can imagine that you have x1, you have x2, and then you have all sorts of paths. Each one of them has, this is like s, this is like s prime. Each one of them gets a different weight, and the path integral, this probability is transformed into a path integral. The advantage is that instead of working with operators, we're now using functionals. So s is a functional of some function x. So we don't need to deal with funny commutation relations, and operator algebra, which is complicated. But the price we pay is that we need to integrate over all possible paths. This is the spirit of the Feynman path integral. And the way you do this mapping is that you take this operator and you break it into many, many small increments. Okay? So imagine that instead of writing this, you write something like e to the minus I delta h times n, where n is basically t over delta. Okay, that's how you construct it. And you can read at your own time how to construct it. It's very straightforward and simple. It's beautiful. And in the end, what you get is that instead of the Hamiltonian, you have the action. And what you know from Lagrange, Hamilton formalism also works here. So the action that appears here is the action that you know and love. Okay? Corresponding to the Hamiltonian that you have here. Okay, so that's why it's so beautiful.
But the Hamiltonian is an operator, and in the
Yes.
mechanics it's a function.
Yes,
So-
functional.
Functional, yeah.
Yes.
So it's not exactly like.
Yeah, true, but you can identify the structure. That's the point. The point is that you write so for example, if you write, if h was something like p squared over 2 you know, plus x squared over 2, and these are operators, then the action that you will get, you won't be surprised that you're going to get mx dot squared over 2 minus, no m is like 1, minus x squared over 2. So you see kind of the weight that each, so you see this is like a superposition of waves. It's like a superposition of waves, and each one of these waves, the amplitude it gets, or the phase that it acquires, is the action of that path. The action corresponding to this image. Okay, so it's a very beautiful concept, but here we're going to do exactly the same thing. We're going to break this e to the minus beta h.
But in the integral that we just erased,
Yes.
d is the functional differential that you integrate.
It's called the measure.
Okay.
Okay, it's a generalization of the differential for numbers, but for functional.
Yeah. Okay.
So what we're integrating over is not numbers. We're integrating over all possible functions, functional configurations. Okay, so here we're going to do the same thing. We're going to write e to the minus beta h as e to the minus delta h to the power of n. Okay, and I apologize for overusing the letter n. Now n is the number of increments that I've divided my operator into, and n, of course, is equal to beta over delta.
And is there an order of magnitude that we want n to be?
Yes, infinity.
But infinity is an, at infinity don't we get the Zeno effect?
Wow. How did he get to the Zeno effect? Zeno effect is related to measurement. It's true that the operator that we're applying here is non-unitary, but it's not a projection operator. Okay? And it's actually you can see that as delta becomes smaller, this operator becomes closer and closer to the identity. So it's not doing, what you're thinking about is performing a projection, a full projection. And we're actually very far from that limit. Okay, so yeah, so what I can do is I can write z as an integral d psi bar psi e to the minus psi squared. Okay, and then I'm going to have zeta psi, and now I'm going to have e to the minus delta h e to the minus delta h e to the minus delta h right? Now what I'm going to do is I'm going to stick a resolution of identity in between each one of these guys. Okay? So imagine that I stick the identity here, and I stick the identity here. But these identities, I'm going to write them like this. I'm going to write them as an integral d psi bar 1 psi 1 e to the minus psi 1 squared, right? Psi 1 psi 1. Okay? And then this guy here is going to be d psi bar 2 psi 2 e to the minus psi 2 squared. psi 2, psi 2. Okay? I'm going to do that all the way to the end. Let me see. Until I get here. Okay? And so we have n of these guys. Okay? So if I have n of these guys, then here I'm going to have d psi bar psi e to the minus psi n minus 1 squared. This is n minus 1, n minus 1, psi of n minus 1, psi of n minus 1. Okay, it's clear? Because here I don't stick one and here I don't stick one. Maybe I will need to stick one. I don't remember now.
Psi n is the coherent state?
Yes. And the reason is because now we're going to switch to the functional. Okay, let me see. I have the fear. Okay, you guys are going to help me out. I might need to stick another one in here in order to really get to the expression, but I trust that you guys are going to be clever enough to identify that. But that's not a big deal, right? Just one more resolution of identity and it's obvious that I can stick it in. Okay, but up to now it's clear? Good. Okay, so now let me write exactly what we have. So we have an integral d psi bar psi. An integral pi j is equal to 1 to n minus 1. I think d psi bar j psi j. Okay. And then I have e to the minus psi. Let's write. It wasn't me. Okay. And then I have e to the minus sum over j is equal from 1 to n minus 1 psi j bar psi j. Right? That's agreeable up to now, I hope. And then we have psi. Sorry, we have zeta psi e to the minus delta h psi 1 e to the minus delta h psi 2 and then we have e to the minus delta h psi 3 e to the minus delta h, and I'm going to write all of them up to n. No, I'm just kidding. And then I have a psi n minus 1 e to the minus delta h psi.
Don't we multiply a lot of things too much?
No, we don't. Next question.
No, because you did both the pi and the multiplication itself.
No. This is like this. Only for this.
Okay.
Oh.
Any other questions? Okay, so now the advantage is that remember that this expectation value, we can just take it. Take it as it is. Because it means that this h is just going to become a functional of psi bar 3, psi 4. So we're going to get something like an integral d psi bar psi pi j is equal to 1 to n minus 1 d psi bar j, like this. And then we have e to the minus psi bar psi minus j is equal to 1 to n minus 1 psi j. And then we have minus some j is equal to, so how many of these we have n? So we have j is equal to 1 to n, and then we have, okay, I'll explain in a moment what I'm doing here. We have what do we have here? We have a minus delta, okay, and then we have h now of psi j bar psi j plus 1, okay. That's basically what we have right now. Oh, no. Sorry. Yeah. Important. I forgot something. No. So, wait. Before we write this, let's be a bit more careful. Okay. Let me do one of these guys. Let me remind you of something. Okay, yeah, this is important. So the expectation value of psi 1 e to the minus delta h psi 2, okay, is, remember that if I write this, okay, then I get basically e to the minus right here I get e to the minus delta h of psi 1 bar psi 2 in this case, right? Because when we computed the expectation value, we normalized, okay? But now if we want to write it like this, psi 1 e to the minus beta h psi 2, we need to multiply here by psi 1 psi 2, okay? And this thing therefore gives us e to the minus delta h psi 1 psi 2 bar, okay? And then, but we also have this guy, which gives us, what does it give us? It gives us plus, maybe? Plus psi bar 1 psi 2. Is that agreeable on everybody?
Beta or delta?
Delta, shit. Okay? This is basically what you see here is just the fact that these are not normalized. So if I take each one of these expectation values, it's not normalized, so we have this extra factor. That's all I wanted to say. So now after I've reminded you of this, now let's indeed take this expectation value. Now there's a question here. There is one thing that's hidden under the rug in this step here. This actually is only an approximate result. And I'll explain to you why. This is also important to comment. because because the Hamiltonian, okay, the Hamiltonian generally indeed so you can imagine that the expectation value here of h or h squared, h cubed, and so on and so forth, it's not the same. Okay, so you know, if I take psi 1 h psi 2, well, we described how to do this expectation value. That's fine. This is indeed, you know, this will be indeed h of psi 1 bar psi 2 times e to the psi 1 bar psi 2. This is fine. This is not the problem. But the problem is what happens at higher orders. So I can't say something like psi 1 h squared psi 2. This is not equal to h of psi 1 bar psi 2, you know, squared times e to the psi 1 bar psi 2. That could have been nice, but it's not. Okay? That's not true. But here, this is where this delta becomes important. Because if this were true, I could have already done this business here. I wouldn't have needed this splitting this e to the minus beta h into small increments. Okay? So this is crucial. This is not the case. Here, this delta saves me. Because basically what I'm saying is that this here I have terms of order delta squared. Okay? And the point is that I neglect this delta squared under the assumption that in the end I'm taking n to infinity. How am I with time? רבע לשש? Oh, so why aren't you saying anything? Okay, so next time, I'm going way too slow probably, but it's okay, it's okay. So next time, we will start from this, we will use this, and I will show you that this thing becomes, we will describe exactly what it becomes. Okay, and that will be the basis which we will, instead of looking at Hamiltonians, we will look at these functionals as tools to study many-body quantum physics. And they will be very useful for us, for example, when we will think about superfluids and superconductors. That's basically the reason I'm teaching you all this, is because of how useful these tools are. Okay, so sorry for all the formalism. It'll take me about 30 minutes in the beginning of next class, and then we can finally talk about some interesting physics. 30 minutes, maybe 45 minutes. No, because we also need to discuss how to do Matsubara sums, which is another headache.